Hey everyone, Rob here from Rising Edge Industries, and this quick take video, I just wanted to run through some of the benefits of the non-volatile memory features in the DR500 data recorder platform, and run through just a quick example, kind of a use case to show the benefits of this architecture in action. And so this is our flagship platform. It's a shock hardened forged differential ended or single-ended channel data recorder. And you can see here, this is kind of a visual representation from one of our application notes, just what the device looks like, and the form factor. They're small, handheld, with an integrated battery pack potted in the unit. And so this quick take video covers actually this application note, which you can pull down from our website, application note 4, power dropout data security. And the intent of this is to show the data security or data reliability during brownouts or complete power loss. And because this is based on a fully non-volatile memory architecture and memory technology, there's no data loss during any brownouts or any power failures for customer data acquired during operation. In this, even if the battery pack is completely removed, the data will still be retained in the unit to be pulled down later. In this application note, we have a couple more signals today. We're just going to run this test with a simple differential sine wave. But the application notes run with accelerometer input as well. On channel 1 has the accel, and channel 2 has the differential sine wave input. And it's a 5-second test. In this video, just for the sake of brevity, we'll do 1 second duration for data acquisition. But feel free to pull this application note down from our website, application note 4, and to go into a little more detail, the block diagram here just describes kind of the top level system architecture of the data recorder, USB connector, voltage sensor biasing, power rails from the power system accessible to the user, 4 analog input channels here on the right, and a discrete trigger. And this is just application note 1. It's just a brief overview of the DR500 platform, so you can pull this down as well. And for this particular video, we're going to focus on the memory system. The pre-trigger memory and post-trigger memory bank are completely non-volatile. And so we're going to acquire data on input channel 1, and we are going to power the device completely off after data acquisition finishes. And we're also going to do a quick example of powering the unit down, completely removing power during a data acquisition cycle. So this will show that complete power loss to the memory architecture, both while the digital engine's operating, acquiring, and storing data, and after the data acquisition run is finished. Both of those cases result in 0 data loss within the system. So the test setup here in the lab is pretty straightforward. We utilize our breadboard, and our breadboard is this whole assembly right here on optical. This is an optical breadboard, and if you buy the breadboard kit from us, it comes with the machined bars and bolts to mount the recorder so it can't move. And this can be transported around, the adapter cards that break out all the interfaces, the cable assemblies, and this I/O card, customer interface I/O card, that allows an easy connection of test equipment, meters, DMMs, things like that. So this is extremely helpful in a lab. It's really great, and we recommend to most customers purchase this just because it makes your life so much easier. Configuring, testing, even getting familiar with the data recorder, training. And so this is a platform we're going to use. Our input into channel 1 comes in here from our signal generator. These are 2 15 millivolt peak to peak sine waves offset by 180 degrees, and they're going to be gained up by 100 when they come in the analog front end. and we'll see a full scale sine wave signal from these two. This would be a representation of a sensor, something like an accelerometer. We have an accelerometer adapter card. These termination cards come with the assembly too that allow customers to terminate these very delicate sensor cable harnesses to a card, so they're much easier to work with, and all this is connectorized. And then we have a meter here just to monitor our 3.3 high precision voltage rail for sensor biasing. We're going to use that to verify that power is cut to the unit, and we're going to do that with there's a power enable button and a discrete trigger enable button. And so this whole assembly, the breadboard kit's intended to allow customers that do purchase a data recorder shown here. This is the one we're going to use for our tests for differential analog input channels. It allows you to mount it securely and break out the interfaces, both for protecting the interfaces from repeated soldering, and it adds a lot of freedom for the customer to test, develop, become more familiar with our product technology and interfacing. And so we're going to use that in this video. So the first thing we'll do to run the test is launch our command and control application, our configuration application. And so we'll switch over to our desktop view here. There we go. And that is, where's desktop view? Okay, so now we're on our desktop view here, and we can see we just opened the link for serial number 25. So there's only one recorder here. We'll get the configuration. And so this configuration is already preset, but to configure a unit for this test, we'll just set the runtime to 1 second, set the gain to 100 for that channel, 500K samples per second on channel A1, and we'll do a set, get configuration. Stays the same, but that's because it was preloaded. And then we'll do a quick double check just to make sure our signal's active. And so this is the DC offset tuning. It's digitally controlled, and you can tune the DC offset of each channel individually from 0 to 3.3 volts. And the view is in ADC codes, so you can go up to from 0 to 4096 for our 12-bit A to D, and we're set at 2038. It's a 1, so this is a little looks noisy because the input's a 1K sine wave, and so the update rate here is around 5 samples per second. It's just for DC offset configuration. It's not for any AC or signal analysis. So the noise is just showing us that the signal's active. And I just want to touch on this quick. You can move the set point of each channel up and down here, offset target and voltage, or in ADC samples. You can see right now we're at 2038, and the range is 0 to 4096. So all that looks good. Close that window and reset the recorder. Erase the post-trigger memory. We're erasing 2 sectors, which will be plenty of space for a 1 second run. You want to reset the recorder before it's triggered every time, and we'll just trigger from USB right now. So we'll do a start. When we click this button, I'll switch over to the other screen on the breadboard, and you should be able to see we have our alive light blinking right here to show the digital engine's ready for a trigger, and it's up and running. The unit's healthy. The LED next to it will turn on for 1 second while it's acquiring data, and the digital engine's operational and out of its idle state. And then the third LED will show that the device has been triggered, so there's a visual LED indication in case you're at a test facility or a test range. You can see what state the unit's in and just make sure your you're up and ready to run and in the right state before you trigger the unit for an actual test. So we should be able to see that. So I'll click now. You can see the LEDs illuminate. The middle one goes off, and the third one stays on. Now we'll download the data file, and we'll switch back over here. You can see the download progress bar is downloading our 1 meg data file. Next, I'll run the little plotting tool, our beta version of the data analysis tool here. Data file is downloaded. Now actually move these to different locations. It rebuilds the file once it's downloaded. Once the download is complete, you got a little printout there to let the user know. So next we'll go browse to the downloads folder for serial number 25. We'll look at the voltage, and we'll open the data file. And so for this data file, we can see the full range signal is there. It's about a 3-volt signal with 2 differential 15 millivolt peak-to-peak sine waves coming in, as we discussed earlier in the test setup. That results in about a 30 millivolt single-ended sine wave, and then that's gained up by 100. And from there we get about a 3-volt sine wave. This looks good. And we've got 500,000 samples of this sine wave for our 1 second run duration. And so now that that's programmed in the data recorder, what we'll do is power the data recorder down completely. So we'll go back to our lab setup over here. We can see it's still shows it's been triggered. The recorder's is a live signal, is up and running. It's back in its idle state. So we're going to power down now. We'll see that this will go to 0, and that will indicate all of the electronics are powered off. You can also hear the device disconnect. If you're a user, you can hear it disconnect the USB interface. Can't hear it on that video, but you'll get an audible alert too. So now we're at 0 volts. The entire recorder is powered down. All the digital electronics in the device are off. The memory chips are completely powered down. Every memory chip in the device is off right now. So we can also see our live LED is not blinking. Our triggered LED went off, and so the data recorder here is completely unpowered. And we'll release the button, let the unit power back up, and we see it's back up and running. It's alive. Our high precision voltage reference here, 3.30 reference, is back up. Looks good. And so we'll reconnect to the recorder, and we'll pull the data file down again after it's been powered off. So we'll switch over to our desktop application, and we'll actually close and rerun this just to show in this video that it will go from the default display signals to, and we'll immediately, let's get config. So our configuration data is all still valid. That's also non-volatile. We'll kick off our download for data file 2, timestamp and date here. All the data files are stored by alphabetical order with the file name in the root directory of where the configuration tools run from, and in that directory you have downloads, and then all the serial numbers that you've downloaded files from are listed here, and then you have ADC code and voltage. So we're just looking at voltage. These are the same sets. It's just that the configuration tool, when it rebuilds one contiguous data file after the complete download, it gives the customer one file in ADC codes and one file in floating point voltage. This is just out of convenience, so customers don't have to convert between the two if they need one or the other. So the file's done. We'll double click, do a replot, and we've got our data here. It looks good, very clean. We'll zoom in a couple times. pretty high data acquisition rate, so we have a lot of sine waves. So this is 1 kilohertz for 1 second, recorded at 500,000 12-bit samples per second into non-volatile memory, and this is our sine wave. So that looks good. So that shows off the main feature here of the non-volatile aspect of this device. I do want to do a little bit more testing. So let's do an erase, and we'll erase 2 sectors of post-trigger memory. We'll reset the device, and we'll do a quick download just to see that the memory system is erased. And then the second test run is a test run to show that even during full speed operation, we can kill power to the unit and the customer loses no data up to the point power was lost. So if you do have a test and you have a brownout or some kind of glitch or a power failure, the data that you have captured up to that point is safe. So let's look at ADC codes. It's a 12-bit A to D sample, but it's stored as a 16-bit word. So what you should see is a 16-bit word, all ones, should be all Fs, and so that will result in a straight line at 65,535, right? So 2 to the 16th is each sample, and that's what we see right here. In fact, we can put our cursors on and see cursor 1, Y value, cursor 2, Y value, and they're both 65,535. So that all looks good. Turn our cursors off. And so let's set up this next test run, which we're actually ready to go. And we're going to start the test, and then we're going to kill power about halfway through. It's not going to be super precise because I'm doing it manually, but the procedure is going to be really to issue a start command with the USB interface, and then I'm going to use the breadboard to kill power manually. So we'll go back to our breadboard display. Just to point this out, we're going to use this power enable button to kill power to the unit. For more information on this, check out our application notes on our website. They describe all of the interfacing, signal characteristics, and the details of what's going on. This video is supposed to be quick and focused really for someone who's familiar a little bit with our platform. So I won't get into that too much right now because it'll take a little bit too much time. This video might get too long. So I'm going to click the start button, and then I'm going to push the power enable as close to halfway through as I can. So you'll see these LEDs up here illuminate and then go out. You'll see this go to 0. This is our high precision voltage reference. This will let us know when the recorder's powered off. So we'll do it on 3, 2, 1, start, and then off. And we'll see where we ended up here. So before I release, just a verification, the high precision reference is off, the data recorder is off, the live light is not blinking, triggered light's off. So everything's completely unpowered right now, and it lost power in the middle of a data run. So this would be equivalent to a failure on a test range or at a test facility, something unforeseen. And so we'll pull the data that we recorded up to this simulated power failure out of the unit and check it. So we'll power back up. Okay, we're now powered back up. We'll relaunch our application tool here. Now you can see the unit's powered up, our live light's back up and running. The device also re-enumerated, and serial number 25 was found by the software at launch. Open. See our battery status is 100% because we're plugged in. And just for completeness, the USB communication and unit charging is all done through the USB link through this. So this is a ruggedized Glen Air connector custom cable assembly with a USB connector on the other end. And so when we talk about the USB interface, it's this link right here, and this is the charging power, where the charging power is supplied as well. So that 100% battery capacity here just shows that the battery's been fully charged to the USB link. And so now we will download our data file. Reset doesn't erase. It's one thing to keep in mind. The erase is controlled through the controls submenu, and the erase menu has sector by sector post-trigger erase or a full memory system erase. And so this should be data file 4. Okay. So now the configuration tool is rebuilding the CSV data file. These are all CSV files, so they can be processed with any customer software application. And we'll double click data file 4, and it looks like I didn't catch it in time. So let's rerun this. Let's rerun this one more time quickly. So we're going to repeat the same process. I'll enable my breadboard camera and the lab bench, and we'll try this again. Okay, see if we got that power back up. Refresh and open. Okay, download. Let's relaunch our application here. Alright, open link. Yep, link's good. Download data file. And I maybe should have done more than 1 second for this video, but hopefully this will work out. So some of the other controls, there's a trigger delay. Oversample is kind of digital averaging. And the sector control for sector erase just allows customers, this is actually really handy, it allows customers to erase smaller sections of post-trigger memory to save time. Alright, our data file is done. Check out data file 5. Okay, so this time I caught it, and it looks like we so we experienced power loss to the recorder right around 600 and right before 630 milliseconds. So we can see this is our 0 to 3.3 sine wave here, and this matches what we had before we looked at on the first test. Full scale sine wave saved in memory. That's right around 3 volts. That looks good. And we had our power loss was experienced right around here. And then what you see is we jump straight up in our data file to what we would expect, which is going to be 65,535. This is in voltage, so it's going to be a little different. Let's open up the ADC code is going to be the same, but your y-axis is going to be in ADC codes. And so we'll zoom in again here because it's right around 0 to 40, about 4,000. So this looks good, and we see our power loss. The samples go from what we would expect in the 0 to 3 volt range. Here, the full scale is 0 to 3.3 volts. And the A to D is ratiometric, and it's powered. Switch back here. So this is the high precision biasing for the sensor also biases the A to D, and so that allows the whole system to be more accurate, fully ratiometric. And so it's so because this is 0 to 3, it's not the full range, but it's fairly close. And so when we get to our power loss here, we see that our data samples jump straight up to 65,535. And we can verify that. Can actually verify that with our cursor. Put our cursors on here. And 65,535, 65,535. So I hope this test was clear. It was a little longer than I wanted it to be, but we got through 2 test runs. The first test run was pretty simple, ran to completion, complete power loss, and powered back up, reconnected to the unit, pulled all of our data out, and we had no data loss. And this test, we lost power in the middle of a test run at full speed, right at a little after 600 milliseconds here, and we went from data acquisition of a sine wave to complete power loss and powered back up, and you can see this data file is broken in 2 parts. Our data file here up to power loss, and then empty memory cells here after power loss. So from a customer's perspective, what you can rely on is not only keeping your data after complete power loss for a complete data acquisition run, but also having secure, reliable data from the instant of the trigger event all the way up to the instant of power loss or some catastrophic failure that would render a lot of current data recorders based on DRAM useless. And oftentimes the test run the customer executed, whether it was a launch test, flight test, based on volatile technology, you lose all of your data on an event like this. You don't get to keep this part, but you lose everything. So for us, it was really important we provide customers with a platform that has secure, reliable data. Every sample or a group of samples is all stored securely, and they can be pulled out reliably. And so that's the point of this video. For more details, check out the application note. In this application note, we use a accelerometer, and we write up a lot more detail of the test setup, configuration, lab test equipment used, and we go through software configuration here. Our lab test fixture for the accelerometer is a kind of a hybrid Hopkins bar. Our data results, there's a little more detail here on just what events are going on inside the recorder, how the engine's working, and what we're actually recording. And we check that out and see something similar when we look at the test run that has a simulated power failure. We also have some SRS spectrum plots coupled here with our time series data. And so this is all up on the website. We have 4 application notes right now, so feel free to check those out, pull them down, and if you have any questions, please shoot us an email or contact us through our contact form.